Okay, today I'm going to talk about adiabatic cooling, and I'm going to show you how it works on these series of pieces of paper here. So let's say this is the Earth's surface. All right, there, that's the Earth's surface. Close enough. It's supposed to be level. You get the idea. Now, under normal conditions, if there's no movement in the air, if the air is just pretty much sitting there, and maybe there's some circulation, some mixing above and below, pretty much what you'll be looking at is the environmental lapse rate. That is, as you rise through the atmosphere, it's going to cool. Now, the average environmental lapse rate for the Earth's surface is about 6.4 degrees Celsius for every 1,000 meters that you rise. So around 6.5 degrees Celsius for every 1,000 meters. That is just the average, however. It can vary significantly depending on the kind of air that you have. Stable air, all right, stable air will have a low environmental lapse rate. That means that from the surface to, say, 1,000 meters, you might change only 4 degrees Celsius. So with stable air, you might have an environmental lapse rate, ELR, of 4 degrees Celsius for every 1,000 meters. For average, as I said, 6.5 or thereabouts is about average. So average might be 6 or 7, something like that. And then if it's really unstable air, this is the kind of air we might get in the summer when we have a lot of heating at the surface, but it's very cold up above. That's not unusual, and this often leads to thunderstorms and other nasty kind of weather. Maybe the difference in 1,000 meters is 10 or 11 degrees Celsius. So let's say under unstable conditions, you've got an environmental lapse rate of 11 degrees Celsius for every 1,000 meters. That makes a big difference as to what's going to happen with the formation of clouds and that sort of thing, and I'll get to that in just a minute. Okay, so that's the start. We're talking about air that's not moving in any particular direction, and we're getting environmental lapse rate, gauging how much difference there is in our temperature from the surface to 1,000, 2,000, 3,000 meters, and so forth. All right. Now let's say, again, we'll look at our surface. Now the Earth's surface does not heat evenly. For whatever reason, sometimes it's a difference in land cover, sometimes it's a difference in how much sun is hitting the surface. Different parts of the Earth's surface warm faster or more than other parts of the Earth's surface. So let's say this part of the Earth's surface warms to 25 degrees Celsius, while over here to the right, it's only 20 degrees Celsius. What's going to happen? Well, air that's warmer is lighter, and it's going to want to rise. And so here's a bubble of air that's 25 degrees Celsius. And it rises very much like a bubble. It stays relatively self-contained as it moves through air that starts out 5 degrees cooler. Now let's track it to 1,000 meters and see what happens. We need to know one other thing before we can track for certain what its temperature is going to be at 1,000 meters. We need to know what the dew point temperature of this bubble is. And I'm going to, just to make things very simple and easy for you, I'm going to say that the dew point temperature of this bubble is 15 degrees Celsius. All right? So it has a dew point temperature of 15 degrees Celsius. That means that when it gets to 15 degrees Celsius, it will have cooled enough that it can no longer hold the water vapor that it is holding, and the water will condense and turn to liquid droplets. Perhaps a cloud forming. Now, what does that mean for us at this point? We're at 25 degrees Celsius. That means we're 10 degrees above the dew point. That means that we're not going to experience any condensation as we first start out. In fact, what we're going to see is a cooling at what is called the dry adiabatic lapse rate. DALR, dry adiabatic lapse rate. You should know what that is. It is 10 degrees Celsius for every 1,000 meters. All right? Now, I haven't talked about the surroundings yet. Let's talk about the surroundings. The surroundings are starting out at 20 degrees Celsius. Okay? And as the bubble rises, it's going to be rising through air that's changing in temperature as well as you head from the surface toward 1,000 meters. I'm going to say that it has about an average lapse rate. I'm going to say that the environmental lapse rate, which refers to the air that's surrounding the bubble, is going to be 6 degrees Celsius for every 1,000 meters. I have simply chosen that as an example. There's nothing set about that. That could be anything. I'm simply giving you that as an example. This, however, the dry adiabatic lapse rate is set. That is set by the way we know this bubble will expand. And as it expands and gets bigger as it gets out toward 1,000 meters, up toward 1,000 meters, those molecules that were packed together are going to be spread apart more. It's the same number of molecules in a larger space. There are going to be less collisions, there's going to be less friction, less heat. It's going to be that much cooler. So we know at 1,000 meters then, it's going to be 10 degrees cooler than it is at the surface. So this bubble should be significantly bigger. I'm not going to draw it a lot bigger than it was at the surface, but it should be significantly bigger. All right. And at 1,000 meters then, my air is going to be 25 minus 10, 15 degrees Celsius inside the bubble. What is the surrounding going to be? Well, it's going to be 6 degrees cooler than it is here. So the surroundings, as you rise through the first 1,000 meters, the surroundings cool to about 14 degrees Celsius. What does that tell me? Well, a couple of things are going on here. One is I've now hit my dew point for my bubble. So if it continues to rise and cool, it is going to create a cloud. It is going to start to condense, and we'll get a cloud forming. To the right, the surroundings, all the air that's surrounding the bubble, is 14 degrees Celsius. It means it's still 1 degree cooler. That means there's still some lift in this bubble. It's warmer than the surroundings. It's still going to want to rise. So let's track it to 2,000 meters. But there's a difference because it has now hit its dew point temperature and it's starting to condense. So we're going to start to see a cloud forming here. And it's going to become part of a cloud. That means as it condenses, what happens to latent heat? When condensation occurs, latent heat is released. That means the cooling is going to slow. It's not going to reverse the cooling altogether, but it's going to slow the cooling down to about 5 degrees Celsius for every 1,000 meters. That's the moist adiabatic lapse rate, sometimes called the wet adiabatic lapse rate. I'll call it the MALR, moist adiabatic lapse rate. That is 5 degrees Celsius for every 1,000 meters. Why the difference? 10 down to 5. It's only half of what it was below because condensation is occurring. The air is, there's water condensing, changing from vapor to liquid, and as it does, that releases heat, slows the cooling process. But we're going to see that that also creates an impetus for the cloud or the bubble to continue to rise. Let's see what happens. So as it gets to 2,000 meters now, it's going to be even bigger. I can't make it that much bigger, but it's going to be even bigger. And it will have cooled by only 5 degrees Celsius. So as it gets to 2,000 meters, it's going to be 10 degrees Celsius. What happened to the surroundings? Well, there's no change for the surroundings. The surroundings are not experiencing anything different. It's still 6 degrees Celsius per 1,000 meters. So from 14, you're going to subtract 6. You're going to get 8 degrees Celsius for the surroundings. Now the bubble is 2 degrees warmer than the surroundings. That means that it is most likely to continue rising, and in fact it's going to rise. It's only cooling at 5 degrees Celsius for every 1,000 meters. The surroundings are cooling at 6 degrees Celsius per 1,000 meters. That means that the chances are it's going to continue to cool slower than the surroundings, meaning that it's going to get even more impetus to rise. It's going to continue to rise high up into the troposphere, where it will probably become part of perhaps a thundercloud, a cumulonimbus cloud, creating thunder and lightning. Okay, so that's how a bubble rises under normal conditions with an average environmental lapse rate. Let me show you one other example. Now, I want to make it clear that I have played with the numbers here. I've kept them simple so that things happen every 1,000 meters. Okay, that's the only reasonable way to do it. If we're talking about intermediate numbers, it becomes very complicated. But for our purposes, we'll keep it simple. Keep it to 1,000 meters. We'll have one other example later where it's a little bit different. But for now, we'll stick with that. All right. Now I'm going to show you one more example, but I'm going to show you actually 3 versions of the same example. So the first, it's going to be the Earth's surface right here. We're going to have a stable example, an average example, and an unstable example. All right? And so let's say that our bubble of air gets to, let's take a different example this time. Let's say our bubble of air is going to warm to 15 degrees Celsius, and our surroundings are 12 degrees Celsius. There's no set number here. There's no set difference. It just depends on the local conditions. Is it going to be 3 degrees difference, 2 degrees difference, 5 degrees difference before this bubble starts to rise? That's very difficult to say. Depends on wind conditions, depends on a lot of things. But for now, we'll just leave it at this. We'll say the same scenario is going to play out in 3 different ways based on the stability of the air. All right. So I'm going to start with the average example in the middle. Now, we need to know one other thing. We need to know the dew point of the bubble, and we need to know what the environmental lapse rates are. I'm going to keep it extremely simple, and I'm going to say that the dew point temperature for the bubble is 5 degrees Celsius. I'm keeping it really simple, folks. Okay? So the dew point temperature for the bubble, 5 degrees Celsius. That's the same in all 3 cases. The only thing that's going to be different is the environmental lapse rate, because that indicates stability, average, or unstable air. So what I'm going to do is going to give this average number 7, environmental lapse rate of 7. So the environmental lapse rate is 7 degrees Celsius for every 1,000 meters of elevation. All right? And we already know what's going to happen with the bubble. As the bubble rises to 1,000 meters, it's going to be above the dew point temperature. So we know it's going to rise and cool at the dry adiabatic lapse rate, which we know is 10 degrees Celsius per 1,000 meters. So as it gets to 1,000 meters, it is going to be 15 minus 10, dry adiabatic lapse rate, 5 degrees Celsius. That's the dew point temperature. What is the surrounding going to be? Well, the surroundings in this case go from 12 minus 7 to 5 degrees Celsius as well. So at 1,000 meters, my bubble and my surroundings are the same temperature. What happens? The bubble dissipates. There's no longer any reason for it to hold its shape. It has no more lift. It's just going to, this boundary between the warm air and the surrounding air breaks down, and you have a situation where the air just dissipates. You might get a little wispy cloud at 1,000 meters, and that's it. You're not going to get much of anything. Let's go to the unstable example. Here, the bubble is going to do just the same as it did here, but the surroundings are going to be different. In this case, the environmental lapse rate will be 10. So my environmental lapse rate is going to be 10 degrees Celsius for every 1,000 meters. That's what we would see in unstable air. Unstable air is much colder up above than it is at the surface. Much, much colder. All right. So the bubble will rise, the same as it did before. Dry adiabatic lapse rate. Whoops, that's an R. It will get to 1,000 meters, and it will be 5 degrees Celsius. We know also that that's the dew point temperature for the bubble. We've got it right here. The environmental lapse rate, however, is different. It will go from 12 minus 10 to 2 degrees Celsius. That means that the bubble is still 3 degrees warmer than the surroundings, and it's going to continue to rise. But notice it's now at its dew point temperature. A cloud will begin to form, and it will continue to rise. But now it's going to rise at the moist adiabatic lapse rate, which we know is 5 degrees Celsius for every 1,000 meters. So it will go from 5, subtract 5, at 2,000 meters, it's going to be 0 degrees Celsius. There's my bubble at 2,000 meters, 0 degrees Celsius. What is the surroundings? It's still going to be rising and cooling at the same rate it did from 0 to 1,000 meters. It will be 2 minus 10 minus 8 degrees Celsius. What are we seeing? 3 degrees difference, 3 degrees difference, now 8 degrees difference, and that difference is only going to get greater as this bubble rises. So this bubble has a tremendous upward momentum, and it will create a strong updraft. So say you were flying through in an airplane, you would feel it very obviously as you passed over this area. You would feel a strong bump upwards if you were, and perhaps some really severe turbulence if you happen to be flying through this area as the thunderstorm was forming, as the cloud was forming. This would definitely help to grow into a large, this would be part of a very large thundercloud that would be forming, a cumulonimbus cloud with the potential for hail and lightning and perhaps even a tornado if it's violent and strong enough as this storm develops. This bubble would rise all the way up to the upper troposphere and create all kinds of havoc, especially if you're trying to pass through. Even underneath, it's going to be pretty violent. All right, so that's unstable air. Now let's go to our example over here of stable air. When do we see stable air? Stable air is when we have high pressure, we have clear skies, very little in the way of cloud formation at all. Very stable air. The air is not that much colder above than it is at the surface. All right, we know what our bubble is going to do. Our bubble is going to rise from the surface and head toward 1,000 meters, and it's going to cool at the dry adiabatic lapse rate. But what about my bubble, my surroundings? My surroundings are now stable, so the environmental lapse rate for the surroundings is only going to be 4 degrees Celsius per 1,000 meters. Very stable air. So my bubble rises to 1,000 meters, cooling to 5 degrees Celsius. Same as it did at all the other examples. But the surroundings, in this case, starting at 12 degrees, cooling to 4 degrees, cooling by 4 degrees, 12 minus 4 equals 8. 8 degrees Celsius. What's wrong? Something's amiss here. The bubble is 3 degrees cooler than the surroundings. What happened? If you want to pause now and think about it, it might be a good idea to do that. I'll keep going, but you might want to pause and think about what happened. If you can think about this and understand it without my telling you, that's great. But I'm about to tell you what happened. The bubble started warmer than the surroundings. It ends up cooler than the surroundings. What does that mean? It means at some point it had to be the same temperature as the surroundings on its way to 1,000 meters. What happens when it gets to the same temperature as the surroundings? Well, we know from over here that when the bubble gets to the same temperature as the surroundings, it dissipates. So I can tell you for sure that this bubble never made it to 1,000 meters. That's why it looks as it does. How high did it get? Well, if you want to try an extra credit question on the midterm, I'll give you a chance. I'll give you a shot at this, okay? So I'll give you a similar kind of question, but you do have to do a little bit of algebra. Not a lot of algebra, just a little. Okay? So let me show you how this works with just a little bit of algebra, okay? All right. How high did my bubble get before it turned to, it reached the same temperature as the surroundings and dissipated? Okay, well, we know our beginning, we're going to have two sides of an equation. We're going to start an equation, we're going to set. We have the bubble side of the equation, and we have the surrounding side of the equation. So for the bubble, the air started at 15 degrees Celsius, and then we know it was going to be minus the change in altitude. Delta H is a change in altitude. I'm going to turn it into an X in a minute. Times my dry adiabatic lapse rate, which is 10 degrees Celsius for every 1,000 meters. Now my surroundings started at 12 degrees C minus delta H, change in height, change in altitude, times, in that case, 4 degrees Celsius for every 1,000 meters. Alright. Well, what I'm going to do is get rid of the thousands right now, and I'll come back to that in a minute. We'll get back to the thousands. We're going to multiply our result by 1,000 to get our final answer. But for now, to simplify things, I'm getting rid of the 1,000. Okay? Just follow me and you'll see what happens. And I'm also going to simplify this equation into a little algebraic thing. So it's going to be 15 minus 10x. X now is my change in height. Equals 12 minus 4x. Again, x is the change in height. Okay. Now I'm just going to solve for x. Right. So I'm going to add 10 to each side, add 10x, I'm sorry, to each side. I'm adding 10x, that's not very clear, but I'm adding 10x there, I'm adding 10x here. And that means 15 equals 12 plus 6x. I am going to subtract 12 from each side. Minus 12, minus 12. I get 3 equals 6x. Now I'm going to divide each side by 6. And I get 1/2 equals x. 1/2 is also 0.5. Now I'm going to multiply by 1,000 to bring the thousands back in that are up here. And I get 500 meters. So, the bubble made it to 500 meters before it reached the same temperature as the surroundings, and it dissipated. So, there you have it. Adiabatic cooling, a bubble rising through a surrounding air, which is very much dependent, surrounding atmosphere, which is very much dependent on whether it's stable or unstable or average. Okay?